All right, welcome back. We started in chapter on kinematics, which is the application of vectors, differentiation, and anti-differentiation, as well as a mix of differential equations. Let's review some of the terms that will be applied to movement of objects or more like particles, which is just single points. Um, just a review about the vector notation and the terms that we're going to be using. So, position, which is a location, which is going to be a vector, meaning that again, it will have a magnitude and a direction. Think about the position as the level on an elevator. It can be above the ground, it can also be below the ground, which would be a negative value. So that implies an opposite direction. Um, the displacement, as defined, it's a vector, which is a change of position. So it's going to be a difference of two vectors of the between the final and starting position independently of its path, which leads to the next one. The distance, which is a scalar value, which is always positive, it will actually depend on the path or the trajectory of the object. So yeah, I'll go into more details with some examples. All right, as you differentiate um, displacement and distance respectively, you'll end up with a vector velocity. Two types. Average is, well, it's the mean, so between a start and end point, and you divide by the duration, therefore, which is that notation, let's say that you would use for the average. Yeah, just checking you can see my mouse. A little bit of notation here. For instantaneous, you use the derivative notation. Um, and with the speed again, it can be split into two. So be mindful, it can be the average or the instantaneous as well. You could also differentiate. Um, but it is a scalar amount, so independent of its direction. Both will have the same units, so it's a distance per time. So those are those two. You need to be familiar with the conversion between the two. And something you might not be familiar unless you do a little bit, you encounter that in physics. Anyway, in calculus, if we differentiate the velocity, we end up with the acceleration, which is going to be in square meters per second if the speed of velocity is in meters per second. Again, it's a vector. It will have a magnitude and a direction, and here's the notation that you will use as a normal regular differentiation. Time again is a scalar amount. Just a reminder, always remember the t variable, the domain, it's always greater or equal to 0. Okay. Um, let's look at the first example. So it's uh, the working out you would do here. It shouldn't be anything that you didn't know before. That would be differentiation and substitution. It's probably just the wording, paying attention to the new terms, the preconditions, and also make sure that you just answer the actual question. So again, just pause that, have a go at determining the values for those questions, and then I'll unpause and I'll continue with the working out. Initial position, so use simple substitution, t equals 0, you substitute to x. So the way you can express it is the particle is initially at O, or the origin. Later on, we'll see that in terms of graphing, if it's a linear trajectory, you would use just a single number line. If it's a two-dimension, you would use a Cartesian plane. Its position when t equals 2, so that's the next bit, you substitute, and notice as it is negative, um, normally your convention is positive to the right, so you would say that the particle is positioned 2 centimeters to the left of the origin. Initial velocity and the velocity at a certain value. So as your displacement is a function of time, you will simply differentiate. You end up with this quadratic rule. You substitute the values to find the initial velocity. Notice, pay attention to the units. So here in that situation, that example was the length r in centimeters. And as it is a positive vector amount, it will be in that direction. For part D, you substitute an x value. This answer this time is negative, so you indicate the correct direction, which is to the left for this question. Now, for part E, as you determine the speed when t equals 2, think about just taking the modulus. So it's an instantaneous speed. So you just take the modulus of that negative 9 centimeters per second, which was the velocity, and then you end up with the answer. Part F, when and where the velocity is 0. So you will solve some equation and you will have to do a substitution. Now the where is you need to find the x value or values, and when you need to get the t values. So first you need to solve that equation. So v equals 0. That's a function of t. It's a quadratic. That gives you two values. You exclude the negative one. So when t equals 1, x is equal to 2. And that is what is answer. Now, the fact that v equals 0, it which is a change of direction, basically. So before that, we calculate a initial velocity which was positive, so which indicates the arrow to the right. So until v equals 0, the velocity is still to the right. It probably reduces to reach 0, and as the time goes on, it will become negative. So it will change direction and go that way. So good practice, good habit to annotate, to do this kind of diagram. So it's a trajectory timeline. So you basically have the uh, multiple information. So you will have your positions number line. You will also need to indicate the time when it happens. And the arrows just indicates the direction of the velocity vectors. Okay. Next example. So it will, from the previous example, as you see, this is going to be, having a diagram like this is going to be critical as you have a change of direction when the velocity is equal 0. And with this new example, that will translate to how you can calculate the distance accurately due to a change of direction. Okay, so here you have a rule for your displacement, which is a quadratic. First part, find the average velocity of the particle in the first 3 seconds, then find the distance traveled in the first 3 seconds, and then you can find the average speed of the particle in the first 3 seconds. So just be careful here as it is relates to the speed and not the velocity. So pause the video, have a go, and then I'll continue. All right, for the average velocity, it's the initial position to the position when t equals 3. So you determine the difference and you divide by the duration, which is 3 seconds, and that gives you your average velocity of 2 meters per second, which is a positive value, which is to the right. Part B, for the distance travel, as it is indicated here, it is useful to show the motion of the particle on a number line, as you're going to have critical points. The critical points are where it starts and where and when it changes direction. So it starts at the origin, which is fun, so you can place your starting point, and then you have a turning point when the velocity is equal to 0. As you're solving it, because you need to, the question is in the first 3 seconds, if you get a t-value that is greater or outside the 0 and the 3, you don't have to worry about the change of direction. In that situation, you differentiate v, that's a linear function, you turn it into a linear equation, you find t equals 1 over 2.5, which is between 0 and 3. So you're going to have a change of direction. At that point, you substitute into the x rule that gives you its actual position. Then from that separates the duration, the first 3 seconds into two intervals. The first interval is between 0 and a half a second. The velocity is negative, so it will be in a direction of it will be to the left, and from 0.5 to 3, v is positive, so it will go to the right. So from t equals 0 to t equals 1 over 2, it's to the left. Change directions towards to the right. Okay. As you substitute t equals 1 over 2, we get x equals negative a quarter. So for the first half seconds, the distance traveled is a quarter of a meter, which is the modulus of that amount. And to find the distance to the right, you're going to be from negative a quarter to the position when t equals 3. You substitute into the rule, that gets you 6. So the particle will have traveled 6 plus that negative a quarter. So it's minus negative a quarter. That gives you 6 and a quarter. You add those two travel over those two intervals. That gives you 6.5 meters. And I will answer the question for, no, hang on, we haven't answered the question. Is that the distance? Let me go back. Yes, so that's fine. That's the distance. And we're going to use that value to find the answer of part C. So for part C, it's the average speed of the particle in the first 3 seconds. We already calculated the distance, and we divide by the duration, and that will give us the average speed in meters per second. All right. So just be mindful with those kind of questions. It's the diagram or the graphing that's going to be critical to make sure you have a good understanding of the problem, and you actually get the right distance, and then therefore the average speed. Okay. Let's move on to the second, another application to go to the second derivative of a function. In motion, it is called the acceleration of a particle. So it's the rate of change of its velocity. So it's the derivative of the velocity or the rate of change of the velocity. Here, the average acceleration, so it's going to be the difference of velocity over the difference of time. And with the instantaneous acceleration, either you differentiate your velocity once, or you go from your position function and you differentiate twice, right? As the derivative of your position in terms of time is your velocity. All right, let's look at a couple of examples. All right, so have a read. Very lengthy, trying to come up with those two diagrams for B and C. Also, you're going to have to do a linear representation of the motion from the velocity and the acceleration. The acceleration graph is additional information to get you a better understanding. And then I'll continue. All right. Position time. So you have your rule here, which is a quadratic. Probably use a CAS calculator. So it's an upside down quadratic. You will find the x-intercepts. You can also determine your turning point. Again, just throw that in your chaos calculator, do a graph trace, or define a rule, solve the x-intercepts, or complete the square to get the turning point form, whichever works for you. Remember, t cannot be negative, so t equals 0 is your initial position. We start at x equals 12. It goes up to the turning point at t equals 1 at a position of 16, and then it goes back that way downwards to towards the origin at t equals 3. As you think about the rate of change, so on this side the rate of change is positive, but it goes to a turning point. So think about it as a the object in that situation, or car. You move to the right, but you're slowing down to a complete halt, sorry. And then what you do is you go into reverse and you go backwards until you reach your starting point, and you keep going in the same left direction. So that's the idea. Um, so it's a quadratic. When you differentiate, that gives you a linear. So your velocity is going to be a straight line. And the derivative of a straight line is a constant. You end up with your acceleration will be a constant acceleration. Right. So those are things idea you need to also keep in mind quickly, so you get an estimate of what your graph will look like. You differentiate. So here is your straight line. Yes, it is negative. So you can see on that side the velocity is reducing. You're slowing down to a halt, and then you go in reverse. All right. As you're slowing down, yes, it makes sense that the acceleration is a negative, which is the gradient. So it's going down. So it's a negative gradient in meters per second per second. Hmm. That reminds me, if I go back to the first slide, I think I made a mistake on the units. Yes. Sorry, my bad. So this is the wrong unit. It is not in square meters per second. It's in meters per square second. All right, so we have our three graphs, which is fine. All right, now the first graph is going to be important, as you see, in terms of calculating the distance. So you need to, let's say for the first 3 seconds, I'm just can't remember the question, but the distance, you need to add two values: the distance traveled over this section and the distance traveled over the second part. As you um, getting back, you have a change of velocity here. Velocity, that's the turning point. So as a number line, you start at x equals 12, you go here, that's your turning point. So x equals 16 and v is going to be equal 0. And then you go into, you're moving towards the left until you pass the origin and you continue in negative directions. So that's fine. I'll continue with that. And the distance travel in the first 3 seconds. So you have uh, when x equals 3, when t equals 3, x is equals 0, t equals 2, x equals 12. So you go, that's coming from this graph. So it's from um, x equals 16. Hang on. Is that a displacement here? Okay, so I'm going ahead, but let's go with the displacement. So with the displacement, I do not care about that turning point. I just have the initial displacement and the final displacement, and the difference. Just be mindful of the sign. So it's gonna be negative 12 meters or 12 meters to the left. For part F, find the distance for the first 3 seconds. Two parts. From 12 to 16, it's 4. From 16 to 0 is 16. Therefore, adding up those two values, you end up with the distance traveled of 20 meters. All right. I think it's gonna be the last example for this part of 10a. Um, Again, have a look at that question. Notice this time it's going to be the displacement is a cubic. You differentiate, the velocity is going to be a quadratic, and the acceleration is going to be a linear function. All right, so we when the position is 0, so that is when x equals 0, you need to determine the velocity and acceleration. So it's about solving equations. You need to first find the t values, which is a cubic. Look for how to solve this cubic. I'm just wondering, how do they factorize it that way? What would be the best way to do that by hand? Probably with just random substitution and using the factor theorem. Otherwise, just cas it. Um, Use the solve function to solve that. That gives you two values again. The fact that t is always positive will exclude the negative answer. You substitute that t value to find your respective velocity and acceleration with the correct signs. So again, they are vector forms. And always answer the question with a worded sentence. Now, this situation, velocity is 0. Important here that you might have to use that later on to determine a distance, as it is going to be uh, a turning point in terms of the displacement. It will be a change of direction, as the particle will change in a different direction, will move to a different direction. Okay, so v equals 0, we replace by the expression of v that gives us an equation in t. We get the value of t. We substitute into x and a, and the position and the acceleration. The position is going to be used when if we need to do a linear representation of the trajectory of the object. Part C, further extension, a equals 0, find the t value, it's a linear expression, it's straightforward, you substitute and you get x and v. Later in chapter 10, we'll talk about the implication of having a null acceleration with Newton's laws, I should say. Hang on, let me see. So let me move myself here. Ooh. So you can see here the working out for question C. All right, so for part D, you notice here there's a turning point. That's when you use the v equals 0. So initial position, move to the right, and then you move to the left, okay? So to find it for the first 3 seconds, from 0 to 1, we move to the right, and then it's to the left, okay? So you substitute t equals 3, which is x equals negative 16. First part of the travel is 2 meters, and then from 4 to negative 16 is going to be that amount, which is 20. So it's a total distance travel of 22 meters. All right, and that's it for this part. And we'll continue with this either online, or hopefully I'll see you all on Friday. See ya.